Welcome to lecture number 1 for EE 206 Circuits 1, Terminology and Definitions. Now, in engineering, especially electrical, we use the metric system. The reason being is you can actually make sense of the metric system. In English, there's a different unit for everything. For example, just to measure distance, there's inches, hands, feet, cubits, yards, ells, fathoms, rods, chains, furlongs, miles, leagues, all units of measure. That creates a problem. Suppose I want to know which is more, a person who's 5'10", or a horse which is 20 hands tall, or a pond which is two fathoms deep. Again, with English, it's really hard to compare when you have different units for everything. Instead, we use metric. Nice thing about metric is there's only one unit. If you want to measure length, the unit is meters. If you want to measure mass, it's kilograms. Time is seconds, charge is coulombs, temperature is Kelvin, angle is radians, that's it. If you want to measure a person, a horse, a bolt of cloth, depth of water, it's all the same. It's all meters. That's the metric system, or System International. The basic definitions, or basic units, are units that don't have any smaller parts. Those would be these units right here. There's also derived units. A derived unit contains several fundamental units. For example, a Newton is a kilogram meters per second squared. A joule, that's 1 unit of energy. That's kilogram meters squared per second squared. A watt is a unit of power. That's joules per second, or kilogram meters squared per second cubed. Amps, volts, ohms, farads, and henries, and so on. Those are the metric units that we'll be using. We also use engineering notation. That's powers of 3 for the exponent. For example, if I want to have 1,000, that'd be 1K, or 1 times 10 to the 3. To give an idea what the scales are, there's a giga, which is a billion. The Earth's population is about 7 billion. Mega is a million, roughly the population of North Dakota. Kilo is 1,000. NDSU's enrollment's 14,000. Milli is 1,000th. Micro, nano, pico. So when we talk about things, we'll talk about millimeters, kilometers, kilometers, picoseconds, and things like that. Nice thing about when you're using metric is if you have no idea what the equation is, you can usually figure it out just by getting the units to match up. For example, this is a typical FE exam question. I've got a piece of copper where the conductivity is 1.68 times 10 to the minus 8 ohm meters. The wire is 100 meters long. The cross-sectional area is 1 square millimeter. What's the resistance? If you have no idea what the equation is, you can usually figure it out. The resistance, I want to get to ohms. So I've got ohm meters, ohms, or meters, and square meters. So if I take ohm meters times meters, gives me meter squared. Divide by meter squared gives you ohms. So just checking the units, what would make sense would be resistivity times length over area, and that gives me ohms. And sure enough, that is the right equation. That's what the units do for you. If you don't know what's going on, you can usually just kind of guess, get the units to match up, and it's right. That's useful later on when we start doing circuit analysis. If I'm doing a circuit and adding a volts plus an amps, that doesn't make any sense. I've got to make sure the units all match up. Volts plus volts plus volts works. Ohms plus ohms plus ohms works. Volts plus amps plus ohms is nonsense. So check the units. Some of the basic definitions that we'll be using in this class. Proton. Proton is part of the nucleus of the atom. Protons do not move in general and are bound in place by chemical bonds. The electrons, we actually aren't really sure what electrons are. We think they're fundamental particles. It's part particle, part wave. The electron is the negatively charged particle, which are locked in place in insulators and free to move in conductors. The electrons are what carry electricity. Note that current was discovered before electrons were discovered, and so Ampere just took a guess as to what direction the particles were moving, and he got it wrong. So likewise, electrons are negatively charged. The direction of current flow is opposite the direction of electron flow. Just because it became standard before we knew what electrons were, we've suffered ever since. Current is the flow of electrons. 1 amp is 6.02 times 10 to the 23rd electrons per second. The voltage is the force that it causes the current to flow, or another way to think of it, it's the energy released when current flows. 1 amp flowing across 1 volt produces 1 joule of energy. And resistance is the resistance to current flow. The basic equation we use throughout electrical engineering is V equals IR. 1 volt is equal to 1 amp times 1 ohm. In terms of voltage, amps, and resistance, think of it like water. If I have a bucket of water raised up high, I've got a lot of head pressure. It's trying to push the water down. The higher I raise this bucket of water, the more the pressure. Pressure is like voltage. It's the force trying to get the water to flow. Current is like the water flowing. More current means more water. And resistance is like the thickness of the pipe. The higher the resistance, the less current flow. We also have conservation of mass. From Einstein, you have E equals mc squared. It takes just a little bit of mass to create a huge amount of energy. If you're not destroying matter or creating energy, then you have conservation of mass. Electrons actually have some mass to them. Likewise, you also have conservation of electrons. For water flow, the water in equals water out. I can't create or destroy water. For electricity, current in equals current out. Or, as my physics prof back in high school used to say, electrons can neither be created nor destroyed. They can only be pushed around. If you have a circuit, I'll be pushing the electrons around. However, they're never created, never destroyed, just moved around the circuit. What that tells you is that if I have a wire that's not connected to anything, I know right away the current is zero. There's no place for the current to go, therefore the current must be zero. In terms of power, watts and joules, power and watts, energy and joules. Power and energy are fundamental properties of a system. Unless you're creating matter, energy is always conserved. And many techniques we use in engineering take advantage of this property. If I can understand the energy in the system, and I understand how the energy changes in the system, I understand the system. I know its dynamics. Another way to think of energy is Newton's 3 laws of thermodynamics. Essentially, the first law says you can't win, meaning you can't get more energy out than you put in. The second law says you can't tie. There are always going to be some losses. And the third law is you can't quit. You may not like it, but that's just the way it is. And there's many types of energy. There's thermal energy. For example, if I have a cup of water, if I put it in the microwave, I add energy to the water, that makes the water hotter. It takes about 4.18 joules to raise 1 cc of water 1 degree Celsius. There's potential energy. If I take a mass and lift it up, I've added energy. If I lift 1 kilogram by 1 meter, I've added 9.8 joules of energy to that mass. There's kinetic energy. When you take your car and hit the accelerator, I'm burning fuel to transfer the energy, the chemical energy, into kinetic energy. Kinetic energy is the energy it takes to move an object. To go from rest to 1 meter per second, it takes 9.8 joules of energy for 1 kilogram mass. And what we care about is electrical energy. It's the energy it takes to move electrons around. 1 joule is moving 1 amp across 1 volt for 1 second. In terms of power, power is watts, power is joules per second. Power is the derivative of energy. So joules per second gives you watts. If I integrate watts, I get joules. Now the notation used in electrical engineering is I have current, voltage, and resistance. The current flows in the plus side of the voltage. In that case, I have voltage is I times R. Power is also volts times amps. If the current's flowing in the plus side, I'm absorbing energy, getting hot. If it goes to the negative side, I'm releasing energy. It's like a battery. Also for circuit notation, there's a thing called a voltage node. Wires have low resistance. If I take a piece of wire and connect 2 parts together, the voltage at this point on the wire is the same as the voltage at that point. A node is all parts of the circuit that are shorted together by a wire or low resistance. So for example, on this circuit, all the red wires are 1 node. The purple wires are one node, the blue wires are one node, and the black wire is a node. So this circuit has 1, 2, 3, 4 nodes. Typically you need a ground reference, so I've got a ground plus 3 other nodes. That'll be important later on. When I want to write equations to solve for the voltage nodes, I need to know how many equations to write. In this case, if I have 3 node voltages, I need to write 3 equations for 3 unknowns. And as I mentioned, ground is important. Voltage without a ground reference is meaningless. For example, we think that the Earth is ground. The birds sitting on a high voltage line think 13,000 volts is ground. They're both perfectly valid ground references. If you short the two together, however, the birds go poof. This is kind of why in circuits, there's a symbol for ground. I could either have this symbol or that symbol. If you see them both in a circuit, what that means is that I might have separate grounds. We think that the Earth is ground. The birds think 13,000 volts is ground. They both work, but don't short the two together because they are not the same. If you do, you get this big bang. A couple other definitions. There's voltage sources. We've got 2 symbols for them. This is a reference to the galvanic cells that were used back in the 1890s. If I take zinc and tin, put them together, I produce a voltage. That's a galvanic cell. Or now when we have a battery, we just use a circle with a plus minus. Either symbol is used. That's a DC source. What this tells me is that the voltage difference between the top side and bottom side is 12 volts. So in this circuit, I know that V1 minus V0 equals 12. Voltages can either be plus or minus. If this is a 12-volt battery, if I connect it this way, with the red leads going up, I'm trying to push current out the plus side. And again, remember, current is opposite electron flow. Current's flowing clockwise, electrons flowing counterclockwise because electrons are negative charged. If I take the battery and connect it backwards, put the black side up here, red on the bottom, I now have minus 12 volts. Either way works. At plus 12 volts, I'm trying to push current through. At negative 12, I'm trying to pull current through. It's like a push-pull. And for voltage safety, if you have a voltage source, the battery is trying to keep the voltage at 12 volts, say a car battery. If you have a wire, I'm trying to make the voltage 0 volts. If you short out a battery, I've got a fight. Battery says 12 volts, wire says 0 volts. Whoever's got the biggest fuse wins. Again, in that case, if the battery wins, you burn out the wire. If the wire wins, the battery gets hot, sometimes explodes. So don't short out voltage sources. Current source. A current source tries to force the current through. This has a symbol of an arrow, and the arrow tells you this is the direction I'm trying to push the current. And this symbol tells me I have 2 amps flowing. The voltage across a current source could be anything. It's whatever it takes to set the voltage. In this case, if I short a current source, that's okay. I just get 2 amps through the wire. If I open up the current source, I'm trying to push 2 amps through an open wire. That, in theory, gives you infinite voltage. So voltage sources you don't short. Current sources you don't leave open. A dependent source. A diamond represents a dependent source. We'll be talking about that a little bit in this class to see where those are actually built. Stay tuned for electronics 1 and 2. Those are used in electronics. An op-amp is a voltage-controlled voltage source, an amplifier. A transistor is a current-controlled current source. And a MOSFET is the voltage-controlled current source. That's how we'll actually build them. In this class, just treat it like a source that depends upon something else. And there's also passive and active devices. A passive device is something that doesn't need energy, i.e. a battery to operate. For example, resistors are passive devices. A resistor limits the current flow. Its symbol is a zigzag line, and the fundamental equation is V equals IR. So this circuit, the voltage, V1 minus V2, is I1 times R1. This voltage, V2 minus V3, is I2 times R2, and so on. And in terms of power, power is volts times amps. It's also substituting V squared over R, or I squared R. For example, if I want to find out the power dissipated by this resistor is V1 times I1, or it's I1 squared times R1, or is V1 squared over R1. Take your pick. They're all the same. The last things for this lecture would be voltmeters, ammeters, and ohmmeters. A voltmeter measures voltage. It's a very high impedance device. Basically, it's passive. You put it across whatever you're trying to measure, and it'll tell you the voltage between these two. Typically, there's a red lead and a black lead. The red lead is a plus, black lead is a bottom. It'll tell you the voltage across this resistor. Voltage leads, a voltage source or voltmeters are placed in parallel with the component that you want to measure. Ammeters measure the current through a device. To get an ammeter to work, what I have to do is take the circuit, cut the circuit, put the ammeter in series, and then measure the resistance or measure the current flow. Again, this is also a passive device. The way it's typically built is an ammeter has a very low resistance, say 0.1 ohm or 0.01 ohm, that I add to the circuit. That 0.1 ohm does change the value of the circuit, but it's small enough not to change it too much. I can now measure the voltage across this 0.1 ohm resistor and calculate the current. Note that ammeters very rarely work in lab. That's because as soon as you take an ammeter and connect it across like a 9-volt source, I'd have 9 volts across 0.1 ohm, 90 amps. That just burned out the ammeter. The last one that we typically use are ohmmeters. Ohmmeters measure the resistance. These are different. These are active devices. Ammeters and voltmeters are passive. An ohmmeter is actually an active. What I do is I apply a test current through the device and measure the voltage. To get that to work, I have to turn off all the other voltage sources over here because if somebody else applying current, it'll change the voltage and mess up my reading. I'm also applying a small amount of current to the resistor, which means if this is an LED, it'll turn on. If this is a firing cap, it'll go off. So voltmeters are actually active, or ohmmeters are actually active. You're applying a test current to measure the voltage, and from that calculating the resistance. And the resistors, there's a standard color code. If you see a resistor, the bands tell you what the value is. The first two bands on a typical resistor tells you what the numbers, like brown means, it's supposed to be orange. This one looking orange. Okay, if that's orange, that's a 3. Black is 0. And red is 2. So that's 30 times 10 to the 2, which is 3,000 ohms. The tolerance is the fourth band. Silver tells you 10% tolerance. So this is 3 kilo ohms plus or minus 10%. That's lecture number 1 for EE 206, Circuits 1, just definitions and terminology.